Okay, so welcome back. Now today we're going to try to understand batteries. Now if you've ever stepped back and looked at all of the different batteries and different types of batteries you use on a daily basis, you may be very surprised. And you probably have been annoyed at some point at all the different options of batteries and trying to figure out how to manage them all. So here you've got just a few of the standard batteries. You've got AA batteries, you've got AAA batteries, you've got 9-volt batteries, you've got C cells, you've got D cells. You've got specialized batteries. This is a USB battery pack. You've got batteries in your computer, your laptop. You've got batteries in radio-controlled devices. You've got all kinds of specialized batteries. And it can be a real task try to understand what they are, how they work, and especially what's the status. Like if I have a battery, what's the status of this battery? And is it even possible to know the status? And then you've got the non-rechargeable and the rechargeable, which means you've got to have chargers. Here I've got two different chargers. Does it matter what charger you use? Do the batteries perform differently? We're going to take a look at that. And we're going to approach this from a practical perspective and look at the actual performance of the batteries and see how they perform over time. And we're going to look at the performance with different chargers and hopefully clear up some of the confusion that you probably experience when you deal with all these different types of batteries and chargers. And to help us visualize how batteries work, how they respond, we're going to use this application that's kind of a modification to an application we developed recently where we turned our Arduino into an oscilloscope. This modification allows us to log data from the Arduino over a long period of time. It's very similar, and I'll probably put up a video in the near future showing how to modify that application to get this logger application. But you can see what we're doing is we've got the battery connected to the input of Arduino, and we're measuring over a long period of time how that battery is responding as we apply load to it. And here we've got like an hour and a half, an hour and 45 minutes worth of data to show how the battery is responding under load. And then when we disconnect the load, how the voltage returns. So this is a really great way to visualize how the battery is responding. And then what you can do is you can send that to a CSV and you can plot the response of multiple batteries or different battery chargers, how the batteries respond after they've been charged by different chargers. So a wonderful way to better understand how these batteries operate. So to try to understand batteries, let's first take a look at a very typical AAA rechargeable Energizer battery. And the first thing we want to do is look on the label and look at the actual numbers. This AAA battery says it is nickel metal hydride. And that is the chemical inside. There are many different chemicals, and that's a whole different science project. For now, it's a nickel metal hydride battery, and it is a AAA. And if you look over here, it says nickel metal hydride, and on the right, it says 1.2 volts. Aha, so that means this provides, presumably, 1.2 volts. And another very important number is down here, 700 milliampere hours, or 0.7 amps for 1 hour. That tells you that this battery should be able to produce 0.7 amps for 1 hour. So what does that mean? Well, let's say I hook up a load across this battery. If you look at these numbers, you might think, well, it's going to always give me 1.2 volts across this load, and it's going to produce for 1 hour 700 milliamps. Well, keep in mind that those are nominal numbers. So if you do a little math, you divide 1.2 volts over 0.7 amps. That says if I've got 1.7 ohms of resistor across this battery, you can expect it to have 1.2 volts across that 1.7 ohms, and the current drawn by the resistor will be something around 700 milliamps, or 0.7 amps, because 1.2 over 0.7 is 1.7. And that's one of the challenges with batteries. Now, first of all, this 1.2 volts is a nominal value, okay? In practice, you're probably not going to see 1.2 volts, as we'll see later. It's going to vary, and it's going to vary depending on how much load you have connected. So it's a nominal 1.2 volts, nominal being in name only. It's just a number, and it's around that when you actually hook up a load. Now, 700 milliamp hours implies it's going to give you, for 1 hour, a continuous 700 milliamps of current. Well, if you've got like a resistive load, the amount of current depends on the voltage. And if the voltage is varying, then the amount of current flowing is varying. So what we're going to see is that since this is a chemical device, its characteristics vary a lot. It depends on what the state of the battery is. Has it been used a lot? If it's been used a lot, then it's not going to give you the rated current for 1 hour. It's not going to give you 0.7 amps for 1 hour if you've already used it a bit. So one of the challenges, you have to figure out, well, what's the state of the battery? Is there any way to figure out the state? How do I know if this battery is any good? So one of the best things you can do is look at the data sheet for this battery and see what the manufacturer says. So here is the data sheet for an Energizer AAA battery, rechargeable nickel metal hydride. You can see nominal voltage 1.2 volts, rated capacity 700 milliampere hours at 21 degrees C. So it depends on the temperature. Again, this is a chemical device, so it depends on temperature. And that is based on a rate of discharge of 140 milliamps of current. So you can see this is starting to be something that gets kind of confusing. And as with most things in the technical world, it depends. It's not a simple device. Since this is a chemical device, it can vary a lot. Temperature, the amount of discharge, how much load is on it. So this gets very complicated. Now let's take a look at some more of the data. It's got a dimensions, and it says it's got an internal resistance. So what this means is if you've got a fully charged battery, it's got 0.1 ohms of resistance, and that's going to affect the output. And you can see here that it's got what's called a discharge characteristic with typical performance at 21 degrees C. And you can see that there are, in these two charts, there are 1, 2, 3, 4, 5 different discharge rates. And it tells you the voltage of that battery over time. And here's 3 hours, 6 hours, 9 hours. And it tells you with a different current or different load current, it will tell you the voltage versus time for different load currents. So here I've only got 70 milliamps instead of 700 milliamps. And then for 140, it looks like it will last for maybe 4 or 5 hours. And then as I increase the load current, here's 350 milliamps, and it might last for less than 2 hours. At 700 milliamps, here's the 1 hour. They're saying 700 milliamps for 1 hour, but you can see the voltage is going to drop when you get to around 1 hour. And at 1400 milliamps, it's going to last for less than half hour. So you can see this gets really kind of complicated, and it depends on a lot of things. So now let's take our Energizer AAA 1.2 volt 700 milliamp hour battery and actually measure its performance. And what we're going to do is we're going to put a 1.7 ohm resistor across the battery, as you can see here. And that should cause, if it's 1.2 volts coming out of the battery, it should cause something like 700 milliamps to flow in the circuit. And what we're going to do is we're going to monitor the voltage of the battery with that 1.7 ohm load using our Arduino and the application we showed in the beginning of the video, C# application. And what we're going to do is we're going to log this voltage across the Energizer battery and see how it performs relative to the data sheet. And then what we can do is we can change the battery, we can do a bunch of things, and we can see how the performance changes. So here we have the results of our testing of two batteries using that same procedure. In the blue, I've got our 1.2 volt Energizer nickel metal hydride rechargeable 700 milliampere hours. And in orange, I've done the same thing, and I've used a 1.5 volt alkaline non-rechargeable battery, and it doesn't have a milliampere hour rating. But as you will see with non-rechargeables, generally they have a higher rated voltage. This is 1.5. So we can look at both of the characteristics using the exact same load, and we can not only look at the Energizer, see how it compares to its data sheet, but also compare it to an alkaline 1.5 volt battery. And you can see here, I've got on the bottom, I've got minutes. And again, this logger is measuring every minute. On the vertical axis, I've got the voltage across the battery and time in minutes as it feeds the 1.7 ohm load. Now, of course, as you can see here, the voltage changes over time. So it starts out, if we look at this Energizer, it starts out a little over 1.4 volts. When I connect the load, it immediately drops to about 1.2, which is its rating. And you can see it only stays there for a moment, and then after 10 minutes, it's down below 1.2, and it kind of flattens out, and this is around 1.1 volt. And then after about 60 minutes, it's down to 1 volt. And after about 60 minutes, or 1 hour, you can see it suddenly drops off very quickly, and the voltage gets down to, in this case, about 0.3 volts after about 70 minutes. So as you can see, the voltage changes over time. It's rated 1.2 volts. You're often not going to see 1.2 volts. Here we've loaded up the battery fairly high with 0.7 amps. If you have a higher resistance or a lower load, it'll probably stay up at 1.2 for longer, but you can see that the voltage varies over time. Now, if you look at the orange, it's a 1.5 volt Amazon alkaline non-rechargeable, and you can see it starts out with no load. It's out around 1.6 volts. As I apply the exact same 1.7 ohm resistive load, it immediately drops down to 1.2 volts, and over time, the voltage drops even more than the rechargeable battery does. So the Panasonic stays up a little bit higher. This drops a lot over time. So again, around over an hour, we're at 0.8 volts. And then in the same way, around 70 minutes, it drops off to almost nothing. You can see it's around 0.1 volt. So again, the battery's voltage changes over time, and it depends on how much load you have. Now, what I also did is after this alkaline non-rechargeable drained down to nothing, this is after 70 minutes, you can see it got down here. After a few hours, I reconnected that alkaline battery to a load, and we can see what the result is for a dead battery. And in red here, I've got the results of this alkaline after it's been totally discharged. And you can see it starts out at about 1.3 volts. And immediately when I apply the load, it drops down to 1.1. And then it drops very quickly down to 0.8. And after about 40 minutes, it's down at 0.6 volts. So this shows that after the battery, the alkaline battery, the non-rechargeable has been totally drained, you can see if you hook it up again, you're going to get basically nothing out. So if we look at the spec sheet, the data sheet for this Energizer rechargeable, here's the 700 milliamps. And keep in mind, we had a constant resistance, not a constant current load. So we had about 700 milliamps, but it's going to vary depending on the voltage across the resistor. So if the voltage is below 1.2 volts, you're going to get less than 700 milliamps. So our curve is not going to match this exactly, but you can see around 1 hour, if it was 700 milliamps, it would be down to almost nothing. And under an hour, it might be around 1.1, 1.2 volts. And in our case, the rechargeable was 1.1 for most of the time, and then at 70 minutes, it dropped down to nothing. And of course, this is because it lasted longer because it was a lower voltage, which means it wasn't a continual 700 milliamps, it was probably 600 milliamps or something like that. So you may have noticed with this dead 1.5 volt alkaline, I connected it to a load right here, this red graph, connected it to our 1.7 ohm load when it was dead, after it had been totally discharged. And you can see the voltage was about 1.35 volts. And that's for a dead battery. This is with no load connected. It starts out at 1.35. As soon as I connect load, it drops down to almost nothing. But this is a 1.5 volt battery. It's dead, and with no load, it's measuring 1.35 volts. So you might be thinking, how do I check if a battery is dead, right? If I just pick up a battery out of a box and I say, well, what's the status of this? Well, you might think, well, it's a 1.5 volt battery and it's measuring 1.35, depending on how accurate your multimeter is. You might think, well, it's almost 1.4, or it's 1.5 rated. That could be a fine battery. Well, that's one of the myths about batteries that, oh, just measured on your meter and it could be good. Well, maybe, maybe not. It depends on how accurate your meter is and what's the status of the battery. So what I did is I looked at what I call the rebound characteristics. I took the same battery and I recharged it completely, and it's a 1.2 volt, 700 milliamp hour, and I ran it through a full discharge. It started out at 1.4 volts, a little over 1.4 volts, and you can see I applied the load. It went down to 1.1. And it stayed that way down to, this is in hours, half an hour, 1 hour, 1.5 hours. And then it finally died right here. And then what I did is I flipped a switch and disconnected the load across the battery. And you can see immediately the voltage recovers. Here's after 30 minutes, the voltage has recovered up to about 1.1 volts. And it's a 1.2 volt battery. So you can see that, if you measure a battery that's 1.2 volts and it says 1.1, it could be dead or it could be good. You don't know. What you have to do is you're going to have to apply a load to it to be certain. And what I did here is I took the battery when it was after a half hour after I discharged it. I connected the load again, and you can see immediately the voltage drops down to almost nothing. And then I disconnected the load and it recovers. So an unloaded battery, measuring the voltage may not give you any good information about the status of the battery. And that's the wonderful thing about the C# application. You can just log the data and you can flip a switch and you can try different batteries. It's a very simple way to actually look at the data. And I encourage you, with any engineering question you have, look at the actual data. That's why it's so nice to write a little application that actually logs the data and looks at the actual numbers rather than going online and asking somebody a question and they may not know the answer, but they make believe they do. So again, you have to be very careful with batteries. That's why what I do with batteries is I always assume that I'm going to use rechargeable batteries for the most part. And I always assume they're dead. So I just recharge them when I need them and start from scratch. So again, one of the big questions you have with batteries is you find a battery lying around, you need it. How long will the battery last? What's the status? Well, as we showed, it depends on a lot of stuff. It depends on, first of all, how much current the load will draw. And then how much voltage the load needs to function. For example, I've got a multimeter. It wants me to put in 1.5 volt alkaline batteries because they generally have a higher voltage than a rechargeable. And if I put in a rechargeable, it's going to get a low battery alarm earlier than I would get for the non-rechargeable alkaline. Does that matter to you? It depends. But if your load needs a certain voltage to function, then your battery may or may not be sufficient. And then how much charge is remaining in the battery? There's a certain amount of charge in the battery, and if you've used some of that, it's like a 5-gallon bucket of water. If you need 5 gallons and you've already used 1 gallon, then the bucket's not going to have enough water for you. You always have to be thinking about the history of the battery and how much voltage your load needs and how much current the load's going to draw. So it gets very, very complicated, which is why, in my view, the best approach with batteries is to get some rechargeables. When you need a new battery, recharge the battery and start from scratch. So now another question is, does it matter which battery charger I get? Again, that depends. For example, I'm taking my AAA Energizer battery And this is the discharge characteristic after it has been charged from dead with two different chargers. One is an Energizer branded charger designed exactly for that AAA and the AA batteries. And the other is a charger that I did a review of a while back. And it's a really nice charger because it charges just about any type of battery. AAA, AA, C cells, D cells, 9 volts. It's really wonderful. And it does it very quickly. It's a 1 hour charge for most of my batteries compared to the Energizer charger, which takes about 12 hours to charge my AAA. The question is either of these better? So what are the results of the discharge characteristic for the exact same battery that's been totally discharged and then recharged with each of these chargers? Here is the results. In orange, I've got my Energizer charger that is designed for the battery. And then in blue, I've got the non-name brand Bonai charger that does it very quickly. And the results are, at least in this case, you can see the orange, which is the Energizer, lasts a whole lot longer. So around 100 minutes, it finally dies. With the Bonai charger, it's, like 60 minutes. But again, you can't take this as absolute. These are chemical devices. They depend on a lot of different things. It's very difficult to say which is better. Everybody wants to know, well, is this better or is that better? Well, in the real world, there's rarely a clear decision. This Bonai charger is very versatile and it does it very quickly. Does it always give you the best discharge characteristic? Well, maybe not. The Energizer is designed for those batteries, and it seems to give a fairly good response. Does that matter to you? Maybe not. So again, you have to know the ins and outs of these things before you make a decision. There's costs you have to figure out. There's a charge time you have to decide. So it really gets very complicated. Unfortunately, with batteries, nothing is really certain. Now, for those who have Simulink and use SimScape in the specialized power systems, there is a generic battery model. If you're interested in doing some simulations, a generic battery model, you can see here, it's under SimScape, specialized power systems, electric drives, extra sources, and the battery. And if you right click and go to help for the battery block, you will get a generic battery model, and it explains a nice block diagram of what's included. It's a control voltage source with an internal resistance we showed before, and it's got the equations here to simulate. And you can also generate a discharge curve, charge and discharge characteristics for different types. So it's got a whole lot of functionality in here if you're interested in doing simulations in Matlab and Simulink. So I put together a quick SimScape model using their generic battery model of the circuit we looked at previously in our bench test using our C# application to measure the voltage across the battery. And here I put in a 1.7 ohm resistor across the terminals of the battery, use their generic battery model. And the measurements I brought out, I just brought the voltage out to an oscilloscope so we can look at this over time. And I set the maximum time up to 4,000 seconds, which should match what we have in our bench test. And again, it's an Energizer nickel metal hydride, 1.2 volts, 700 milliampere hours. If you double click on it, you can see you can select what is the chemical composition of the battery. I selected nickel metal hydride, 1.2 nominal voltage, rated capacity in amp hours is 0.7. And initial state of charge is 100, and battery response time responds to a square wave, I think. And just apply that, and what it will do is will take those nominal parameters and develop its own discharge curve. You can tweak it if you want, but once you fill that in, you can hit plot, and it will give you a nominal discharge characteristic at the 140 milliamps that we saw in the data sheet. And you can see at 140 milliamps, which we haven't measured on the bench, but this is what you can expect, that the voltage will stay high and then drop down below 1.2 at just under 5 hours. So what we're going to do, we apply that and we're going to run the simulation. And the simulation's done. We're going to check on the scope, and this is the response at a resistive load of 1.7 ohms. And you can see it starts out, here's 1 volt, here's 1.5 volts, so it's probably 1.4 something. And it stays around maybe 1.2, 1.25 for most of the time. And around 3,500 seconds, here's 3,600, which is 60 minutes or 1 hour. You can see around 1 hour, it goes down to 1 volt. So we can compare that with what we measured on the bench. And here is the results of the bench test. And you can see it starts at 1.4, which is about where this is. This actual test hangs around 1.1 volt for most of the time. And this one's around 1.2, 1.25 for most of the time. So this one's a little bit lower. So we can look over here at 3,500 seconds. It's around 1 volt, and here is about the same thing. It goes down to around 1 volt and then drops quickly. You can tweak the parameters, you can do what you want, but you can see that you can do a reasonable model in Simulink to model a battery. So I think this is about it for the battery discussion. If you like any of these videos, please hit the like button and subscribe, hit the bell notifications, and most of all, please let others know that we're here so we get some more views. Really appreciate it. Otherwise, take care and have a really good day. Thanks.